So today's lesson has really very little to do with geometry. It's pretty much pure probability. So some of you are going to really like this because I don't think there's any areas or shapes or anything involved here whatsoever. Independent events. Probability. This is a pretty important topic in probability for two events to be independent. Basically, two events are independent if the outcome of one event does not affect the outcome of the second event. For example, flipping a coin and rolling a die. I mean, I can flip a coin, I can roll a die. Whether I get heads or tails in the coin has no impact on the outcome, what happens when I roll a die. So those are independent events. So let's say we have two students, or a student taking a quiz randomly, and they randomly guess the answer to 4 true-false questions. So does what they guess on answer 1 and what they guess in answer 2, are those independent events or are they dependent events? Okay? Are the two guesses independent or dependent? And the way to think about this is, you know, they got a 50-50 shot on question 1. And question 2 is exactly the same thing. They got a 50-50 shot. It doesn't matter what happened in question 1, whether they got true or false, or whether they were incorrect or incorrect. It has no influence whatsoever on the second question. It is an independent question. There are questions in the same test, but they're completely independent situations. So yes, those would be independent events. Here's a scenario. A group of students includes 1 boy and 3 girls. Student randomly chooses one of the students to be a speaker and a different student to be the recorder. Use a sample space to determine whether randomly selecting a girl first and randomly selecting a girl second are independent events. Well, so we could say, what happens? Okay. What are the different things we could do here? So we have 1 boy and 3 girls. Okay. So if we select a girl first, okay, so first we select a girl, sorry. Okay, then what do we have left? Well, selecting a girl first, if I select a girl first, then we have 2 girls left and 1 boy. So the chance of selecting a girl second becomes 2/3, and the boy second becomes 1/3. Okay, just simple probability. 2 out of 3 left are girls, 1 out of 3 left are boys. Is selecting a girl first different? Is the probability different for selecting a girl first? Well, we started out with 3 girls and 1 boy. So the probability of selecting a girl was 3 out of 4. Probability of selecting a boy is 1 out of 4. So notice the probabilities are different of selecting a girl first versus selecting a girl second. That tells me that those are not independent events because the probability has changed. Based on what happened the first time, it influenced the probability of what happened second. That's not independent events. We call those dependent events. Okay? Determine whether randomly selecting a girl first and randomly selecting a boy second are independent events. Again, we notice that the probability of randomly selecting a girl first is 3/4, and a boy second, because you already selected 1 girl, is 1/3. That's different from selecting a boy first. So therefore, again, dependent events. Okay, because the outcome of one event affects the probability of the next event. Okay, that's the idea of dependence, not independence. Core concepts here: probability of independent events. If 2 events are independent, if and only the probability of both events occurs, the probability of the events. Okay? So, again, if P of A and B is the probability of A times the probability of B. So that's one way of defining independent events. So if we're going to spin a spinner with 5 different colors, red, green, blue, yellow, and white, all with equal area, and then flip a coin, what is the probability of getting a green and a heads? Well, so according to my formula, probability green and heads. By the way, we always use very descriptive things in probability to say exactly what we're going to get. And this is how we notate it. P, green, and heads, equals P of green times P of heads, because they are independent events. Probability of green, there are 5 different colors, each with equal area. So in a fair spinner, the probability of green would be 1/5. Probability of heads is 1/2. So the probability of getting green and heads is 1/10. 1 out of 10 times, I will get that. Or if you want it as a decimal, 0.1, or as a percent, 10%. I could express probabilities as a fraction decimal or 10%. How could I model this? Again, pretty easily. Wouldn't be too tough to model. Zoom entire page. There we go. That's what I need. So I could say I have red, green, blue, yellow, white, and then each of these gets a heads and tails. Tree diagrams are very useful models. How many of these outcomes result in a green and heads? Well, green, the only ones are here, and heads. The only outcome that is green and heads is right here. That's one outcome out of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 possible outcomes. It's another way of finding that probability by making a model. Dependent events. If 2 events, A and B, are dependent, then the probability that they both occur is the product of the probability of the first event and the conditional probability of the second event, given the first event has already occurred. Okay? So the probability of girl first and girl second from another group of problems, there's an example too that we didn't see, but in this example, there are 9 girls. It looks like, and 3 boys. Okay, based on just what the numbers I'm seeing here are. I'm trying to think about this one as I'm going live here. So, but anyway, probability of girl first and girl second. Well, the probability of a girl first was 9 out of 12. Okay. Probability of girl second, given that a girl was selected first, well, there's still 8 girls left. The numbers seem a little funny here. I guess without seeing the actual example, this is a little bit of a tough one. Let's take a look at the next one. Tell you what, we'll just move on and take a look at the next example. As part of a board game, you need to spin a spinner which is divided into equal parts. You find the probability you get a 5 on your first spin and a number greater than 3 on your second spin. Okay? This is a standard probability problem. What is the first off, we need to determine, are these independent events or these dependent events? And one way to determine that, one way to think about that is, if I spin it the first time, does the result I get the first time eliminate possibilities for the second spin? So like if I spun this spinner and I got a 1, does that mean 1 is not possible anymore for the second spin? I have a reduced set of possible outcomes? Well, no, I don't. The outcomes are exactly the same. So since the second event has the same types of outcomes, I haven't reduced them by what happened the first time. I haven't removed somebody from the pool or removed a possible outcome. Then they are independent events. So I have to calculate that probability since they are independent. So again, my formula, P of A and B equals P of A times P of B. And I'm going to let you calculate this probability as part of what we're doing. Now that you've done it, let's just go ahead and show what we got. The probability of 5 on the first spin is obviously 1 out of 8. The probability of a number greater than 3, well, that would be 4, 5, 6, 7, or 8. So there are 5 of those spins, and your second spin is 5/8. So that would be 5 out of 64. And that should be your answer. Hopefully that's the one you picked. By the way, if you put that as a percent, you could calculate that out. It's not that there's a fraction in the result. A bag contains 21 bills and 5 $100 bills. You randomly select a bill from the bag, set it aside, and then randomly draw another bill from the bag. Count the probability that both events will occur. Now, are these events going to be independent or dependent? Well, it's pretty obvious if I draw a bill out of the bag and I keep it, or I keep it out of the bag, that when I reach in the bag to draw a random bill out the second time, the probabilities have changed because that one bill is now missing. So because there's a missing bill, these are dependent events, because the outcome of the first event affects what the outcome of the probabilities of the second event. So let's take a look at this. What is the probability that the first bill is a $100 bill? Well, that's pretty easy to figure out. I have 21 bills and 5 $100 bills. So there are 5 possible outcomes that I want out of 25 total, or 1/5. Okay? What is the probability that the second bill is a $100 bill? Okay? And again, given that the first bill picked out was a $100 bill, there are now how many $100 bills left in the bag? Well, there are 4. Out of how many total bills left in the bag? There are now 24 bills left in the bag. So that's 1 out of 6. Okay? So the probability of A and B is the probability of A plus the probability, or times the probability of B given A. So 1/5 times 1/6 would be 1/30 of getting 2 $100 bills. What's the probability that both bills you draw out are $1 bills? So start over on this one. And I'm going to let you calculate this as your second question. What is the probability that both bills are $1 bills? Remember, it has to be P of a $1 bill. Okay? And then P of a $1 bill given that a $1 bill was selected the first time. We're going to multiply those two. That's the probability of A and B, and you can go ahead and do that, and we'll check that answer. Let's go ahead and check that. The probability of a $1 bill, there were 20 out of 25 were $1 bills. Okay, so that's 4/5. Now, after I chose that $1 bill the second time, there are now 19 $1 bills remaining out of 24. Okay, so I'm going to take 4/5 times 19 out of 24, and 4 times 19 is 76. Actually, I can reduce this right away. 4 and 24 reduces to 1/6. Just a little math here since I'm multiplying. So that's 19 over 30. So 19 out of 30 times you will get 2 $1 bills. 1 out of 30 times you get 2 $100 bills. There we go. You randomly select 3 cards from a standard deck of 52 playing cards. What is the probability that all 3 cards are hearts when A, you replace each card before selecting the next card, and B, you do not replace? Okay, if I replace the card and just draw a new random card each time, those are independent events because the probability does not change because we're selecting from the same data set each time. If I do not replace cards, then they are dependent events, which means because it changes the probability because my set of possible outcomes has been reduced by what happened first. Okay, if I don't replace the cards and I need to get 3 hearts, well, hearts are 1/4 of the cards. There are 13 out of the 32 cards, so it's 13 out of 32 times 13, or 52, sorry, out of 52 times 13 out of 52, or 1/4 times 1/4 times 1/4, which is 1 out of 64. Okay. So the probability of drawing specifically 3 hearts is 1 out of 64. Okay, that's if I replace the cards because, again, every time we had that's when they're independent events with replacement. If I go without replacement, the first one is 13 out of 52, but the next time there are only 51 cards left in the deck and only 12 of them are hearts. Next time, there are only 11 hearts left, and there are only 50 cards left in the deck. So I got to take 13 times 12 times 11, which is 1716, over 52 times 51 times 50, or 132,600. So if I take 1716 divided by 132,600, that's 0.0129. If I can change that to a decimal, let's see if it'll let me do that. Or to a fraction. Nope. It's 11 over 850. To reduce decimal, or about 0.013. 1.3% chance. Here I've got 1 out of 64, which is about 0.015. 0.016, rounded. Okay, so with replacement, I do have a much higher probability, well, not much, but I do have a higher probability of getting 3 hearts. Okay, how about the probability of no hearts when we replace, when we do not replace? Well, that's just going to be the complement of each of these, so no hearts would be 39 out of 52 times 39 out of 52 times 39 out of 52, and 39 out of 52 times, now there'd be still, there are 38 no hearts left out of 51 times 37 no hearts left out of 50. And we could go ahead and calculate those. Quality control inspector checks for defective parts. The table shows the results of inspector's work. Find the probability that a defective part passes, and the probability that a non-defective part fails. Okay? So given that a part is defective, what is the probability that it passed? Well, the probability of it being defective, if we look at this, we had a total of 3 plus 36, that's 47, it's 500 total parts. So we want to get at our marginals here. Okay, so it's 39 defective out of 500. I have 461 non-defective parts out of 500. I have 453 that pass inspection and 47 that fail inspection. Find the probability that a defective part passes. Okay? So the probability that it is defective and passes is the probability of defective times the probability of passes given defective. Okay? So the probability of a defective part is 39 out of 500. The probability of it passes given that it's defective. Okay? Well, the probability of passing given defective, 3 out of 39 pass. So the probability of passes given defective, passes and defective, picking a part that is that you randomly pick a part that is passive, that is defective, and it passes is simply 3 out of 500. Okay? So if you randomly pick a part, and that is a defective part, and it passes, the probability of that happening is 3 out of 500. Okay? In the interest of time, I'm going to cut to the last problem. At a school, 60% of students buy a school lunch, only 10% of students buy lunch and dessert. What is the probability of a student who buys lunch also buying a dessert. This one can be solved kind of an interesting way, okay? Because sometimes the formulas get interesting. But let's say we have 100 students in the school. So we're going to make a little tree out of this. We have 100 students. So we have some students that buy a lunch and some students that buy no lunch, don't buy. Okay? How many of them buy lunch? Well, 60% of them do. So 60 go here and 40 go here. It says 10% of students buy lunch and dessert. So if they buy lunch, now this is a question of buy lunch and dessert. These also buy dessert. Okay, so that's 10 of them, which means the other 50 do not buy lunch and dessert. They just buy lunch only and not dessert. We don't know how many of the no buy lunch might actually buy a dessert. We still have our total 100 people. What is the probability of a student who buys lunch also buys dessert? Well, what do? We know that 60 people bought lunch, 10 of those people bought dessert, so 10 out of 60, or 1/6. Okay? So we can model it just using numbers. Probability is kind of a tricky thing. And honestly, it is one of the trickier things that we work on even in Prob and Stats in AP. So just something to keep in mind as you're working through it. Most of the problems aren't that hard, but I want you to look at things, work on modeling things. It's going to be a bit of a challenge, but that's okay. These are important topics that often show up on ACT tests and stuff like that. So sorry for the long podcast again, but that's what's going to happen when we're cramming this stuff in.